So in this video, we're going to look at the expected value, the expectation, and the variance of a DRV, a discrete random variable. The expected value is simply a fancy name for the arithmetic mean, or the mean, and often we see that written as E of x. When we want to calculate it, we use our PDFs and our probability distributions, and it's very simply, we add up all the values of x multiplied by their probabilities. So in this example, first of all, we're given a probability distribution. It's in our table, and we're asked to find A. Now the first thing is nice and straightforward, is that we know that all the probabilities add up to give 1. So I know that 0.2 plus 0.4 plus 0.3 plus A equals 1, and very quickly we see that A equals 0.1. Now, we're then asked to find the expected value of x, the mean of x. And the way that we do that then is E of x, capital X, is equal to, well, first of all, it's this column, so the value of x is 1, and we multiply that by 0.2. So it's 1 times 0.2 plus the second value of x, 2, times its probability, 0.4, plus the third value of x times its probability, plus the fourth value of x times A. And in this case, we know A is 0.1. So it's 0.2 plus 0.8 plus 0.9 plus 0.4. And when we put those all in, we get an expected value of 2.3. So the mean value, or the value that we'd expect to get when we roll this dice or toss this coin, whatever it might be, roll a spinner even, is 2.3. So a second example, same sort of thing. We're given a probability distribution. This time we're actually given the expected value of x as 2.91. And we know that the expected value is x times its probability, x times its probability, x times its probability. And so again, we can quite quickly say that E of x is, and if you want to write it down, the sum of x times the probability that x equals x. That's the definition of it. Now, the E of x we know is 2.91. This x, first value of x is 2, multiplying that by its probability, 0.49. The second value of x is, we don't know, but we're going to call it A, and we're going to multiply that by 0.31. And the third value of x is 5. We multiply that by its probability, 0.2. So 2.91, when we work this through, we get that's 1.98 plus 0.31a, and eventually then we get that A is equal to 3. So that's the expected value of x, or the mean value of x. Another quality that we want to look at is what's called the variance, and it measures the spread, or helps measure the spread of data in statistics. And it's very closely linked to standard deviation, which we may have seen before. Standard deviation being the spread of data, and variance is simply standard deviation squared. And we can use the expected value to help us get the variance of a discrete random variable. And it says variance is the expected value of x squared minus the expected value of x all squared. And just be careful here. These two values are completely different. The expected value of x squared and the expected value of x all squared. This expected value of x squared means we work out what x squared is, and then we multiply it by the probabilities and add them up. This is, we take the values of x and multiply it by its probabilities, and then square the overall answer. So here's an example. A random variable z has the following probability distribution. And we're first of all asked to find what expected value of z is. Well, the expected value of z is going to be the values of z multiplied by their probabilities. So it's 1 times a quarter plus 2 times an eighth plus 3 times a half plus 4 times an eighth. And when we work through that, we get that that's 2.5, 5/2. So that's the expected values of z. However, we're asked then to find the variance of z. And if you remember up here, we have the variance is the expected value of x squared minus the expected value of x. Now we've got this second bit here already, it's 2.5. We're going to square that later. But the first thing that we would want to find then is what's the expected value of, in this case, z squared. Well, if z is 1, z squared is 1. And so if z squared is 1 multiplied by the probability that goes with it is 1/4. When z is 2, z squared is 4. And we're going to multiply that by the probability that goes with it. When z is 3, z squared is 9. And we're going to multiply that by the corresponding probability. And finally, when z is 4, z squared is 16. And we multiply that by its corresponding probability. And when we work through that, then we get that the expected value of z squared is 29/4. Now, to get the variance, we know the variance of z is equal to expected value of z squared minus the expected value of z all squared. Well, the expected value of z squared we got to be 29/4 minus the expected value of z we got as 2.5, so 5/2, and we're squaring that. So 29/4 take away 25/4 is 4/4, which ends up as 1. And so the variance is 1. Finally, last thing, the standard deviation. Well, the standard deviation is just the square root of the variance. So in this case, it's √1, which is 1. So that's finding the expected value and the variance of a discrete random variable. However, we can also use these rules that I've just put up for you to help us work out quite quickly variables that are linked to probability distributions that we've already worked out. For example, if we know what E of x is, and we're asked to find E of ax, so every value in the distribution is multiplied by a, then a quicker way of doing that is simply you multiply a times E of x. The expected value of a constant, if you just have a constant time and time again, then it's just b. The expected value of 2 and 2 and 2 and 2 and 2 is just 2. And so if you have the expected value of ax plus b, what we can do is then we can say, okay, whatever we do to x, we multiply it by a, and then we're adding b. So we're going to do the same to the expected value. We're going to multiply the expected value by a, and then we're going to add b. So multiplying and adding values to any set of data does exactly the same to the expected value. It multiplies that expected value by that value and adds on any value. However, when we're dealing about the spread of data, adding and subtracting values to every set of data, every value in a set of data doesn't do anything to the overall spread of data, because if some of the top values have 3 added to them and the bottom values have 3 added to them, the spread of data is still exactly the same. It's only multiplying that affects and dividing that affects the spread of data. And it would if we multiply every data item by a, then the standard deviation gets multiplied by a. And that means that the variance, which is the standard deviation squared, actually gets multiplied by a squared. So the variance of ax, we can quickly say is the variance of x times a squared. The variance of a constant, well, if you just have a constant and a constant and a constant, it's the same constant every time. There's no spread in the data, there's no change there. And so when we put those together, the variance of ax plus b, adding and subtracting does nothing to the variance, but multiplying does by a square factor. So the variance of ax plus b is the variance of x, just multiplied by a squared. This plus b has no effect on it. So when we look at this e of 3z minus 1, the expected value of 3z minus 1, we find the expected value of z to be 2.5 up here. So that makes life much quite easy, because rather than multiplying every value by 3 and then taking 1 away from it, we can just say that this is equal to 3 times the e of z, take away 1. And 3 times, well, we worked out the e of z was 5 over 2, take away 1. And when we do that, we get 13 over 2. On the other hand, if we want to find the variance of 3z minus 1, well, this is the same as the variance of z multiplied by 3 squared. The minus 1 will not affect the variance. Adding and subtracting doesn't do that. So this is 9 times, what did we work the variance to be? 1. And that's equal to 9. Much, much quicker. I guess we could have gone back to these tables and said, okay, 3z minus 1. Oops. If z is 1, then 3z minus 1 is 2. If z is 2, this is 5 and 8 and 11. And we could have found the expected value of 3z minus 1 by saying, okay, 2 times a quarter plus 5 times an eighth plus 8 times a half plus 11 times an eighth. And when you do that, you do indeed get 13 over 2. But that's quite a long-winded method. It's okay, I suppose, when we have just 4 values, but if you were to have a lot more of them, this is much, much quicker way of doing it, especially when we've already worked out the answers for e of z and the var of z as well, or the variance of z.